We've done it. We're here. It's the last one in 4.1 of our text. Our last thing about max and minimum values, but it's not the last time we're going to play around with max and minimum values. This is just our lead in. Remember, we're in 4.1. This is just laying down all the scaffolding so we can actually get to work and learn about the mean value theorem and a few other fun things. So let's start getting after it. We're going to do two different topics. We're going to take a little pause on the way through here and just remind you about the extreme value theorem, saying that if f is continuous on a closed interval, then we're going to get a max and a minimum value. Just a reminder, continuous, closed interval, max, minimum value. Somewhere in that closed interval. Okay, we'll be back to that. We learned about critical numbers. And then we have this one little slide that's letting us know that if f has a local max or min at C, so local mins and maxes, they're critical numbers where they happen. All right? It's not a two-way street. It's not a two-way street. This doesn't go backwards. But if local max or min, then critical number. All right? It's in your text. Look it up. We're going down to our closed interval method. So, the closed interval method is just using the extreme value theorem. It uses extreme value theorem, EVT. We'll have an IVT. Oh shit, we have an IVT. Next, we're going to learn NVT. So EVT, the extreme value theorem. So in order for us to find the absolute max and min of values of a continuous function, I swear we've heard that somewhere before, on a closed interval, we're going to do 3 steps. 1, 2, 3. First, we're going to find the values of f at the critical numbers of f and f of f in AB. So f prime of c set equal to 0. You'll find those c values. That's what we're going to do there. Critical numbers. Huh? Because we're not going to really give a shit about the ones that don't exist, because if they don't exist, then we wouldn't have had a closed interval that was continuous and be a function. So now number 2, we're going to find the values of f at the endpoints of the interval. So we're just going to plug in the endpoints. F of A, F of B. No derivative, none of that shit. We're just going to plug it in. Just F of A and F of B, and we're going to see which one's biggest and which one's smallest. Cool. And then the last step is we're just going to check and see what's the biggest and the smallest. Actually, the smallest values of the absolute min. Yeah, not much to it. Let's get after it. So using a problem from your text, I dig this one. I usually put it on quizzes, but can't really do that with you now. This would have been your quiz problem afterwards. So let's take a look. It's number 59 out of your text. Now we want to find the absolute max and min. So those are our 2 games. So our absolute max and our absolute min. Now these are y values that we're trying to find. We're just trying to see what the highest point and the lowest point. And let's assume that we're not going to be able to draw a graph of this. I don't look at this immediately and go, oh, clearly this is how the graph works. Not at all. This is challenging, but we do need to have a little bit of knowledge about it. We need to know that this is continuous upon its domain and that we have a closed interval. But we have our closed interval. It's from 1/2 to 4. And the domain of these 2 functions being multiplied together, well, the domain of x to the negative second is just everything but 0. And then ln of x, its domain is positive values. So we're good to go. We're only dealing with positive values over here, and that interval does not contain 0. Hence, it must be continuous because we have the multiplication of 2 continuous variables. All right, cool. So we can start this problem. So step 1, which is saying we're going to want to go take f prime and go find those values of c when it equals 0. So let's go take a derivative on this. So f prime of x is equal to... let's do a little product here. So let's leave the x to the negative second alone. Let's take a derivative on ln of x. And if we're leaving it as x to the negative second, I'm not going to write 1 over x. I'm going to write x to the negative first, just to stay consistent. So plus. Now we need to take a derivative on x to the negative second. So the negative 2 is going to fall there, and that's going to change that sign in the center. So we get negative 2x to the, lose a power, negative third. And we didn't take a derivative on ln of x. So now let's clean this up. X to the negative second times x to the negative first. We add, and we get x to the negative third. 1 over x cubed. But now when we look over on the other side, we have an x to the negative third as well. They have the same denominator. So it becomes 1 minus 2 ln's of x. If you need to show the intermediate steps, you need to show the intermediate steps, but I'm going to jam right past. Now we know that the denominator here is x cubed, so we can't have it equal 0, but that's not in the domain of our function anyway, so I don't give a shit about it. So we're just going to take this, set it equal to 0, and we're going to try and solve for our values of x. Let's add the 2 ln's of x over to the other side so we don't end up with negatives. Now the algebra is going to get a little tricky here. Let's divide it out, so we get ln of x is equal to 1/2. Now here's what we do. To get that x out of the argument of the natural log, we're going to need to treat it as if it's an exponent, or do a circle trick, but I don't want to do the circle trick with you. We're going to treat it as if it is an exponent, and that it's an exponent, and both of them have a base of e. What this does is the inverse of the natural log of x is e to the x, so when we take e to the ln of x, this merely pops out x. And then we are left with e to the 1/2 power, which is the same thing as x is equal to the square root of e. Boom! So let's put this thing underneath a list of suspects. This goes underneath a list of suspects of values that we can plug in. They're going to give us a max or a minimum value. So there's our first one. Boom, we found it. There's a suspect. We're going to need to plug that thing in later. Our other suspects. So now we go to step 2. Our step 2 is we just want to plug in endpoints. And then step 3 is going to compare to see which ones are the largest. Well, our other suspects are hanging out right here. They're 1/2 and 4. It's the only other 2 options that we could possibly have. So we're going to plug those in. Those are our other 2 suspects, 1/2 and 4. So we're going to need to plug in all 3 of these. So step 2 says just plug in the endpoints, and then step 3 we're going to actually plug in our the value we found, that square root of e. But now we just want to check it. So we're going to plug in our endpoints first. But we're plugging in our endpoints, notice I'm writing in blue, into f of x, not its derivative. So let's do that with 1/2 and 4. So we get f of 1/2, and that's equal to, and I'm going to clean this up a little bit. I'm going to call it ln of 1/2 over x squared. So this becomes 4 times ln of 1/2. And without a calculator, I'm pretty sure I can solve this thing at least pretty clean. Kind of clean. I don't know. Did you know that, you know this is negative? Let's try something. ln of 1 minus ln of 2. ln of 1 is equal to 0. So really we're left with 4 times negative ln of 2, or negative 4 times ln of 2. There's f of 1/2. Let's just circle this thing. We'll come back to it later because we're going to have to compare. So we found some negative number. You could punch it into a calculator, couldn't you? You could check that. But I know it's negative, so even without a calculator, I don't think we'd need that. So now let's plug in 4, and we're going to get ln of 4 all over, now it's just that x squared, so we're just going to square it up, and we get 1/16. So we get that f of 4 is equal to just 1/16 of ln of 4, or maybe you don't like the way I wrote that. Maybe we write it as just ln of 4 divided by 16. All right, well, you can punch that in a calculator. I think that's less than 1/10. I think it's pretty freaking small. ln of 4 is like right around 1, a little bit bigger than 1, because the base is e, 2.71 or something. It's just a little bit bigger than 1 over 16. Shit, it couldn't be any bigger than a 1/10. No way. So we have a negative value, something negative, and then we have something small, but it is positive. So we've done step 2. We've looked at our 2 suspects, 1/2 and 4. You know what? We need to do our step 3, and we need to compare all of these things. So let's take that last thing. We need to compare, but in order to compare, we still need to plug in our root e. So let's go find out what f of root e is going to equal. So let's plug that into our f, sorry about that with the color. Let's plug that thing into the f, not f prime. So we're going to say f of that root e is equal to, that's ln of root e over root e squared. So this is, what the heck? This is ln of e to the 1/2 power over e. Well, the 1/2 falls to the front, and I think we get 1 over 2e. 1 over 2e. Oh, sweet, I think we found it. So we have that f of the square root of e is equal to 1 over 2e. E being about a little smaller than 3, but let's say it's 3. Should say it's 2. The biggest this thing could be would be a 4th. The smallest this thing could be would be a 6th. But that shit's still going to be bigger than that. And that. So, well, you know what? I think we found our absolute max. Our absolute max. Our abs max is going to be our f of root e is equal to 1 over 2e. Punch it into a calculator and double check that your teacher isn't out of his mind. And then for our absolute min, I think it's going to be that 1/2, considering that shit's negative. It's the only one that's dang negative. You know what I mean? So there we are. We have an absolute max. We have an absolute min. We found it by using the closed interval method. Use a calculator to prove it to yourself that those truly are. But that's not absolutely necessary. I think you can do pretty much most of these problems without a calculator. I don't like those decimals. But for these, if you want to use them, and go for it. And now this is going to conclude our chapter 4.1 section, or section 4.1, not the chapter. So, you're going to come back and this is going to say 4.2. Good news. We'll see y'all soon.